Hi everyone, welcome back. In this week's lesson, we're going to be talking about motion. We're going to break this down into a two-parter. So in this first video, we're going to just recap some basic ideas about motion in code, and we'll talk about a new concept called vectors. Vectors can get pretty deep, so we're not going to dive into the math of it as much, but we're going to learn, we're going to start to get acquainted with the concept of vectors and how we can apply that in our projects. And especially as it comes to programming motion. We'll see these are very useful objects to know about. Once we tackle motion in the first part this week, in the second part, we will take this idea of making things move. We will scale it up by making lots of objects move on the screen, and we'll connect it back to last week's tutorial on Perlin noise. So we're going to use Perlin noise to affect the motion vectors of our objects and kind of create interesting movement from there. All right, so let's start with just talking about basic motion. So up until now, if you followed an introductory P5JS course with me or somewhere else, the way that we represent the position of an object on screen has been using variables. For example, we could define a position as an XY coordinate, and then maybe in setup, we'll give these some values. By the way, I went ahead and already added window width and window height to this blank sketch. Let's set a black background here, a white stroke, pardon me. And we're going to use these two variables to draw something. Let's draw a rectangle. Add XY and give it a size. By the way, in P5JS, if we only give one dimensions to rectangle, you get a square. Right. So this should be pretty familiar. Let's turn off the fill as well for now. Okay, so here's our white rectangle. And this is how we've been representing coordinates. Okay? Now, one thing we can do is we can represent coordinates when we're programming using what's called a vector. A vector is an object that comes with P5JS. It also represents a mathematical concept. There's a whole branch of mathematics devoted to vector math. As I said, we're not going to dive into the math today, but we're going to learn about the vector's various abilities, its various superpowers, and how they can help us write simple motion, simple animations, things like generative drawing machines. So if we were to represent this coordinate, this position, as a vector, we would do something like this. Instead of creating two variables for xy, we're going to create a single object. We're going to call it position. So I'm just making this name up here. And then in setup, we're going to say position equals create vector. Now, a vector is going to be an object that's going to have internally an x and a y coordinate. So let's give it an x and a y coordinate to start with, like we had before. Yeah? And then instead of drawing the rectangle at x and y, we're going to say position.x, position.y. Yeah? And we're back where we started. So by doing so, what we're doing is we're creating a vector object. Right? So let's open the vector reference page. So this is from the P5JS reference. We're creating a vector object. We're using the create vector function. Vectors in P5, by the way, can have 2 or 3 dimensions. So all that stuff works in 3D as well. And once we have a vector object, we can see that it contains a few fields. We have X, Y, and we're not using Z here in this example. And then it comes with a bunch of functionality. Those are the vector's abilities. We're going to explore them in today's example. There's various things we can do with vectors. Some of these things are particularly useful when we're trying to program motion and drawing. For example, we'll be able to look at a vector and ask for its direction using the heading function, right? Or calculate the length of a line represented by a vector, or take a line and rotate them using the rotate function. So lots of very useful abilities that would be a little bit more complicated to program if we had to write this object from scratch. Okay, so jumping back to our sketch here. So now that our position is a vector, right? Traditionally, when we talked about motion in a program, it went something like this, right? We said in order for us to have motion, we need to have change over time to the position of something. So if I wanted to move this object along the x-axis, I might do something like add 1 to the x field of the position vector, right? And now this object is moving along x. Or we could say, move it along along y at the same time, right? Interesting. B5 is telling me position as a reserved word. I didn't know that. I didn't think it was. Okay, never mind. All right. So this gives us some basic motion, right? Now, because we're moving along the x and the y axis, right? We need to add a quantity to both x and y. We could also think of the amount that we're moving in each frame. We could also think of representing that as a vector, okay? Because a vector, remember, is an object that has an x and a y inside of it. So imagine we created a second vector here, and we're going to call this vector velocity. Okay? Fancy word, but basically it means it's just the motion, right? The amount of movement we're going to apply to an object. And today, in this first example, we're basically building like kind of a physics-inspired, simple movement framework. So we're going to have concepts like position, like velocity, and we're going to add one more to this in a bit. So let's create this this second vector. Right? We're going to say velocity equals create vector, and we're going to give it, let's say, 1 and 2, what we have down here. And now we're able to write something like this. We can say position.x plus equal velocity.x, velocity.y. And we can get our rectangle to move. Okay. So again, I'm not sure why I'm getting this warning here about position being part of the language, but you know what? I'm just going to ignore that for now. And I'm going to keep using position and velocity. Sometimes I like to use, in my own programs, I like to write POS for short and vel for short, but I think that makes things a little bit harder to wrap our heads around. So we're going to just spell out the entire words here in this example, just to make the program as clear as possible. So if we can add x to x and y to y like this, the other thing we can do is start to take advantage of the vector object's abilities. Now, one of the things we can do when we have vector objects is we can add them. Okay, so the vector object has an add function where you can take one vector, another one, and add their x, y, and z if you work in 3D components to one another. Okay? So in other words, what we're doing here is we're doing vector addition. So because we're working with vectors, we can rewrite this as such. We can say position.add velocity. Pretty neat. And now we're back to where we were before. So already I kind of like this because even, this doesn't seem like a huge benefit or a huge jump, but I just want to point out two interesting things that are happening in our program. First is we're now packaging the XY variables for our object into a position concept, a velocity concept. So now they're kind of bundled in the same object because these coordinates, they will always go together. So that makes sense. And then now we can start to write code like this. We can say position, add the velocity to the position, right? So this is a lot easier to read than the version where we have to spell it out like this. So the other benefit is we're going to be able to write more concise, more articulate, simpler code by relying on those vector operations. So we can add the position to the velocity to our position, and we get movement. Okay. Now, just so we can see a little bit better what's going on with these vectors, let's spend a couple of minutes here just visualizing the vectors, because in a second we're going to add some code that's going to allow our object to follow the mouse, and we're going to do that using vector math, and it's going to be helpful to just see a little bit what's going on. So I'm going to create a function here. I'm going to call it show vectors, and this is going to be temporary code in our program, so I'm putting it in its own function. I just want to quickly add some code that's going to draw the vectors on screen so we can see a little bit what's happening. So a vector in math, I promise we wouldn't delve into the math, but we're going to just do a tiny little bit. The concept of a vector, the way I like to picture it in my head, is it's basically an arrow. Okay, so it's a construct that represents an arrow, and an arrow has always two ends because it's a line with a direction. The anchor, the base of the line, is always going to be the 0, 0 point. Okay? And the tip of the arrow, the other end of the line, is going to be the xy value for our vector. So if we were to draw, for instance, with a white stroke here, if we were to draw our position vector, we could represent it as such. We're going to draw position 0, 0, and then position.x, position.y. Okay? So this is kind of a representation of our position vector. Okay? And why don't we also, while we're at it, let's set rectangle mode to center. And that's going to mean that the position of our little square here is actually going to be at its center. It's going to be a little easier for other stuff we want to do down the road. So we now have our position as a vector. Okay? And actually, let's make these random too, just to mix it up a bit, because let's make it random between -1 and 1 for both x and y. Just so that the movement is different every time. Maybe I was getting bored of it. Now we're going to draw a line to represent our velocity vector. Okay? Now remember, we're adding velocity to the position. So what we're doing is we're saying go to the end of position and add the line represented for by velocity. So that means in order to represent this, the 0, 0 point of velocity is in effect is going to be the end of the position vector. So we're going to use push and pop here, and we're going to translate to position.x, position.y, and then we're going to draw, let's say, a green line. Just so we can tell they're different. We're going to draw a green line that goes from 0, 0 to velocity.x, velocity.y. Normally I wouldn't draw these vectors, but this is just for explanation purposes. Now this line here is going to be very, very tiny. Remember, our velocity vector is just small values. Otherwise, if we made these values really big, the square would move really fast, and things would get a little crazy. So what I'm going to do here is just cheat a little bit so that we can see the line. I'm just going to multiply the values. So it's not the real vector, but at least we'll be able to see it with our eyes without requiring a magnifying glass. And we can kind of see, it's a bit small here already, right? So in fact, let's make it even larger. Okay. So you can see that there's a green line. I'm going to keep refreshing the sketch here. The green line here is our velocity vector, and we can see that the square is moving in the direction of the line, right? Because we're adding this quantity to the position. Right? So the two vectors, right? When we're adding two vectors together, the result is we're getting a new vector, a new position, which is kind of the sum of the two lines put one after the other. So this is a way to picture what vector addition is doing. Okay, so and then we'll keep using that show vector bit as we add a little bit of complexity here. So our vector here, remember the actual vector is really tiny. I just magnified it here for show. So we said vectors have superpowers. They have abilities that we can use. Add, obviously, not a very exciting superpower. Another very useful ability of the vector object is once you have a vector, and you can read through the list at some point just to get an idea of what's possible, but we'll point out some of the most useful ones. Some of them you can skip over, like dot and cross. This gets into more complex geometric calculations, and we're not going to dive into this. But there is a very useful function called heading. Okay? So if you have a vector object and you want to know which way it's pointing, you can use its heading function. So let's use that here. We're going to ask for the heading of our velocity vector, and we're going to use that to set the rotation of our square. So when we draw our square, what we are going to do is we will say push and pop. We're going to translate to position.x, position.y. This is important because if we want to be able to rotate an object around its center, we have to bring the origin to the center of that object. Now we draw a rectangle at 0, 0. Okay. And we are also going to throw in some rotation. Let's say rotate, and we're going to use velocity.heading. So this is the angle of the velocity vector. So this is very useful because now we can easily draw something, and as it's moving, we can rotate it, we can align it so that it's facing the way that that object is moving. Okay. So pretty neat. So we get that kind of for free just from starting to shift our thinking in terms of representing our position and motion and speeds as just loose variables like x, y, and speed x, speed y, starting to shift our thinking to representing these quantities as vectors. It kind of unlocks some new things that we can do. All right, so let's build on this. Let's add a behavior to this program. We're going to apply, we're going to try to steer, instead of making the velocity random, we're going to get this square to try to follow our mouse cursor. Okay? And we're going to do this using vector operations. So the first thing we'll do in order to be able to tackle this is we are going to represent the location of the mouse cursor also as a vector. So let's create a vector here. I'm going to create it in draw as a temporary variable. Let's call it target, and we will create this vector using mouse X, mouse Y. And just so that we see what's happening, let's go into our little show vector function. We will draw a line from 0, 0 to target.x, target.y. And if you're paying attention, this is just basically going to be mouse X, mouse Y. And let's set a different stroke, a color that we can see, maybe blue. All right, what did I do? Oh, yes, of course. So I've made target a local variable, so let's not do that. Let's make it global then. We'll make target a global variable and get rid of the let here. Because yes, if I define it in draw, it's only visible inside the draw function, and show vectors doesn't know about it. All right. So now we have a vector that is representing the blue line is the vector from 0, 0 to our mouse cursor. We have a vector that is our position. So if we wanted to know the arrow that goes between these two lines, right? If you picture what we want is we want a velocity vector that is a line going from our square to the tip of the blue line, right? This is the velocity that would take us towards the line, towards the blue line. So to find this vector, it's very easy. We just have to do vector subtraction. So when you subtract a vector from another, what you get is basically the line between them, right? The line between them that gives us, this is what we use subtractions for. So let's create here, we're going to create a temporary variable to hold that difference between the two vectors. I'm going to just call this variable diff, and we will say target dot sub for subtraction, the position vector. So we're going to subtract the position of our object from the target, okay? And that's going to give us the line that should go from the position to the target. Okay? Now, one thing to point out here is if I do this, if I look at sub here, there's two ways that we can subtract. If I click on the sub function, right, the method, there's two different ways we can use it. We can use it as what's called a static method, or we can use it as an attribute of the object. So if I do it like this, this is actually going to modify the object on the left, right? So as I subtract, it's going to modify the value of the object on the left. Or I can call this version, right, which is saying take these two vectors, subtract one from the other, and then return a brand new vector as the result. Okay? So if I do this, what happens is you can see that my blue line is kind of gone now, right? My blue line is leaving because we can't see it, but the blue line is now showing the direction. This is changing my target vector. So we could rewrite this using p5.vector.sub, and we will sub target and position like this. And now this is no longer affecting my target vector, but we're still getting the difference. So the difference is going to be a line that goes, we can picture it as a line that goes from the end of this square to the blue line over here. So let's see if we could draw it maybe. We're going to draw it as, we're going to use push and pop, and we're going to do the same as we did for the velocity. We're going to translate to the position.x, which is the end of the line position, and then we will draw our diff.x, diff.y, and let's set a red stroke maybe for that one. Now, if I try to run the code, I'm going to run into the same issue again. So let's make this a global variable as well, just so we can see, right, the difference. And this is what we get. Okay? So we can see that our red line is now going to be a vector that will allow us to, if we use that as our velocity, it would push us towards the blue line. Okay? So just like we have currently our current velocity is the green line, but if we use the red one, right, we could see how this would take us towards the mouse cursor. So let's try it out. Instead of, let's make the velocity of our object equal to, let's make it equal to this difference, okay, and see what happens. Cool. So now we got the square to follow the mouse cursor using vectors. Okay? Now this behavior, this motion, it's a little jittery, a little glitchy, as you can see, and that's because we're using, we're making the velocity quite large, right? By saying use the entire distance from the end of the line, from your position to the mouse cursor, and we're basically trying to just teleport over there. Instead, if we cut that, if we made that vector a little bit smaller, right? We're going to rein it in a little bit. This would allow us to kind of start moving in the right general direction, but not necessarily get all the way there right away. So that will open up the door for creating maybe more interesting behaviors. So one way that we can scale this difference vector is we're going to multiply it by just a number. If we multiply the vector by a number, it's going to take that number and multiply both the x and y component by it, effectively just scaling it. Okay? So imagine if we multiplied it by 0.5, right? Now you can see that we're lagging a little bit behind the white line, right? So it's not getting there instantly. We could take that a little further. Maybe we'll go to 0.1, right? So now in essence, what's happening is we're setting the velocity of the object, right, its speed. We're calculating the vector that goes from where it is to where the cursor is, and saying just take that vector and shrink it, right? Make it 1/10 of what it's supposed to be so that we're not going too fast. And then we get this behavior. And of course, our green line is huge because it's being exaggerated when we are drawing it down here. Now that we are being a little bit more reasonable with our velocity, maybe we will get rid of the scaling and we can see it a little bit more realistically. You may not be able to see because it's quite tiny, but the green line now represents our velocity, and yeah, we can see it as it goes faster. We can see it getting bigger. Very cool. All right. And we can tweak this value to kind of affect the behavior. You know, if we make this number really, really small, it's going to take a long time for our square to eventually catch up, but it will, and it will also kind of slow down as it approaches because we're always splitting the difference. Cool. All right. Okay, so let's add one more idea to this motion model, and then we're going to talk about just kind of tidying up our code, and then we'll wrap it up for this first example. So the next idea I want to add to our motion model here, now that we have position and velocity represented as vectors, and our basic motion idea is we're adding the velocity to the position. Okay? I want to add one more concept to this, which is going to be this idea of acceleration. The way we're programming things right now, we're a little bit limited because we are here automatically making the velocity, right? We're overriding the object's velocity with this new kind of difference vector, direction vector that we calculate based on the mouse cursor position. What that means is that down the road, we won't be able to have more than one force affect an object. For example, we might want to have this object follow the mouse, but maybe in our simulation or a drawing machine, maybe we want to also add gravity or wind or have some other objects in the scene kind of have an influence on the motion of that object. So in a simple kind of physics-driven motion simulation, we might want to have more than one force have an impact on a particular object. So the way we're going to represent this in code, we're going to take the simplest approach that we can, and we're just going to add one more concept to our motion equation. So we're going to say if motion is like adding velocity to the position, in other words, we have a change over time in position, we're going to add that concept to the velocity itself, and we're going to call that acceleration. So velocity, right, is the rate of change in position, and acceleration is going to be the rate of change in velocity. So the idea is that in every frame, we are going to start with a blank acceleration. So we're going to say acceleration dot mult 0. So if we multiply anything by 0, it becomes nothing. And then instead of making the velocity automatically equal to the force we want to apply. Instead, we are going to, actually, let's move this down over there. We are going to take our acceleration and we are going to add the force that we want to apply our object to it. So now we have a place where we can kind of pile on, we can add multiple forces if we wanted to. And then eventually we will take that total of the forces that are going to be taking place in a particular frame. And in this simple example, we just have the influence of the mouse, but in future examples in this series, things will get more interesting. We will take this acceleration and we will add it to the velocity. Okay. Then once we've done this, we will take our velocity, add it to our position. So we're kind of adding one level of indirection here, and you'll see why in a second this is interesting. All right, but first I need to get rid of my errors. Yes, of course. So I've defined a variable called acceleration, but I also have to create the vector object. So we will say acceleration equals create vector. And let's see what happens if we put no arguments. It should give us a default value of 0. Okay, so very interesting. This is what our motion looks like now. So we can see that we are still kind of following the mouse, but we are circling it around like crazy. And the reason this happens is because we've added this layer of indirection. Now we have a place where we can set the forces we want to apply to our object. We can add them to this vector, and then we take that and we add it to our velocity. However, there's kind of no friction in this simple universe we created. In other words, the velocity is free to continue to increase and nothing is ever bringing it back down. And in the physical world, obviously, there's all sorts of, there's friction from the air. You cannot have just pure infinite velocity. So this velocity is going to have something kind of taming it, bringing it back. And in our program, we're going to think of that concept maybe as friction. Okay? So the way that's going to work is we are going to say, once we've added the acceleration to the velocity, we're going to tell the velocity to chill a little bit by multiplying it by something that's going to make it a little bit, it's going to scale it down a little bit. Okay, so that's going to be our concept of friction. Let's start with a number like 0.7. Let's call that friction. And just remember here, this is our easing for the follow behavior. So let's see what that looks like. Okay. All right, so now already we can see that the springiness has diminished. Okay, there's still like some spinning around that happens once we've reached the target. We can make that number lower, right? So the lower the friction, that's kind of counterintuitive, but the lower the friction, right, the most friction we have, the lower the number. So a 1 here means we're multiplying by 1. Okay, so there's no friction. And a low number means there's a lot of friction. Okay? In fact, instead of multiplying, maybe it would make sense to divide, right? Divide by a scalar instead. Yeah, that's more logical. Instead of multiplying, we're going to divide so that the 1 here would be, wait, no, that doesn't work. Okay, never mind. Let's stick to multiplication. So 1 here is no friction whatsoever. And then a small number here is a lot of friction, right? Because we are taking our velocity and we are artificially shrinking it a little bit like the way the easing is working on the difference vector here. Sort of the difference between these two is that in our model, right, our easing only applies to this force here that we're applying to our object, whereas the friction is something that's going to apply to the total. Okay? So once we have multiple forces, not all of them will have easing, but we're always going to apply some kind of friction here just to make the system not go too chaotic. And as we reduce the friction, basically we end up with like almost like a spring effect, okay? Which could be interesting as well. Maybe that's what we want. All right. But let's go with like a lower number here for friction, and here's our behavior. Okay. All right. So let's take a second here and recap what we're doing. So what we're doing is representing motion, right, in our program using vectors. That's the whole point of this first exercise. So we've taken the time to create a position, a velocity for our object, and even an acceleration. So we have these three quantities that are going to work together to allow us to program simple motion. And then to demonstrate it, we've added a basic behavior. Let's add a comment here, which is follow the mouse. Okay. We have our model of motion here, which is adding forces to the acceleration, taking the acceleration, adding it to the velocity, but then chilling the velocity a little bit so things don't get out of hand, and then ultimately adding the velocity to the position of the object. So this is our basic kind of motion model. And then here we're drawing our object so we can see what's happening, and we're using the velocity vector's ability of being able to tell us what's your angle, right? Because it's a vector, it has some very useful abilities, including the heading function. What are those abilities? They're all listed on the vector reference page. So if you want to learn about what other things the vector is able to do, for example, we could get, if you want to know how long, what's the length of a line represented by a vector, we could use the mag for magnitude function. So it has some very useful functions. Another one that's handy sometimes is this idea of normalizing. So you can take any vector and you can cut it down so that it will have a length of 1. And then from there, it becomes easy to scale things, right, to a particular size if you know that you're starting from a length of 1. So this is called normalization. Okay? You can also limit the magnitude of a vector. So all kinds of useful operation that we can do once we represent our concepts in our program using vectors. You can take two lines and get the angle between them, right? So all kinds of geometric operations that are very handy if you're going to be programming drawing machines in particular. All right, so we've done all of this, and then we have a little bit of code here that was showing us the vectors. I think we can now maybe take that out, and all we're left with here is the behavior of our little square. Okay. Now, before we wrap up this first lesson, we're going to take a second to clean up our stuff here, because while we did this demo, this code has gotten pretty messy. So we're going to leave things in a good place in order for us to start the next lesson, where we will take this idea of a moving object and we're going to scale it up by creating hundreds, thousands of them, and creating a framework for that. So let's talk about how we could clean up this code a little bit, and then we will wrap up this first lesson. So the first thing we're going to do is we're going to say, okay, we have this moving object, and really it has 3 variables that belong to it. Okay. Whereas the target and the diff here, these were all about calculating this behavior for following the mouse. So these are kind of like their own thing. Okay. But our object is really represented by position, velocity, acceleration. So we're going to take these things and we are going to bundle them into one package. We could call this package anything. Sometimes you could refer to it as like a particle. We could call it a mover. I'm going to use the word agent for this series, just because it flows well. I like saying agent as opposed to particles. Particles gets kind of annoying saying it over and over. So we're going to think of our moving object as an agent. So we're going to take these 3 concepts, position, velocity, acceleration. We're going to package them into one single object called an agent. So we have some options here in JavaScript as to how we might want to structure this. We could create a basic object, which is in JavaScript just a collection of variables, or we could use the class syntax. If you've seen my previous series, we've used classes to represent objects. Just to show you a different way of doing things, we're going to stick to a basic object, and then we will simply rely on creating functions that will then take these basic objects we create and just manipulate them, transform them. So rather than use a class, a more kind of we're going to use a bit of a hybrid between an object-oriented approach and a functional approach to writing the program, just to show you a way of working. So let's talk about bundling these. So the way that we could do this is we're going to create a function. So let's go outside of draw here and above show vectors. We don't need this anymore. We're going to create a function. Let's call it create agent. Okay? And the job of that function is going to be to return an object. So we're going to return an object, and actually just to make it extra clear, we could just straight up return the object, but instead I'm going to just really spell it out here. Normally I wouldn't do that, but just to demonstrate, we're going to create a temporary variable. Let's call it temp. Right? And then we're going to make it equal to this curly brackets. So in JavaScript, this is the notation for declaring objects. And then when we're done, we're going to return this temporary variable we created. So what are we going to put inside this object? Well, we're going to put position, velocity, acceleration. So we're going to say position, okay, is going to be equal to create vector. And we'll come back and put parameters in there in a second. We'll say velocity is going to be equal to create vector. And remember, this is a syntax for creating attributes of an object. We use the name of the attributes, then the colon, then we use the whatever value we want it to be, whether it's a number, the outcome of a function, the name of a function, whatever it is. Then we put a comma to separate the list of attributes, and the last one is going to be acceleration. So this is like the type of syntax that you're likely to make mistakes with. So just be very careful and deliberate about how you structure this, and make sure again that you have an open and closed curly bracket. You use column to separate the name of the attribute of the object and its value, okay? And you use commas to separate each line. Okay, so just be a little careful. And even though we don't need it, I like to end with a comma anyway, because later on, if I decide to add a fourth object, I will just be able to keep going and I won't forget to put my comma over there. Okay, so that's just what I like to do. Now we could create we could put in some initial values for the parameters. Okay, maybe the velocity will start at 0, the acceleration will start at 0, but it might be nice to have a way to tell when we create an agent where we want it to start on the screen. So let's make those XY coordinates. We'll make them parameters of the create agent function. And then when it's time to create our position vector, we will use those values that we can provide when we first create the agent. Okay? And yeah, so we could have just returned this part, okay? But just to make it extra clear, I'm showing you that all we're doing is creating an object variable and then returning the value. Okay? So let's see what the implications are in terms of our code here. So let's now we're gonna ditch these, okay, and we're gonna replace them with a single agent. And then in setup, right, we are going to go here and say agent equals create agent. That's our function we just made up down here. And create agent wants X and Y. So let's just give it a X and Y to start with, like we had before. Awesome. And then of course, if I hit play, I've just broke the rest of my code here. So we'll get to that right now. So what we've done is we've taken velocity, position, acceleration. We say these belong to an agent. Let's package them together in a single object over here. Remember, what we're doing here is our program worked, but it was a mess. So we're just kind of tidying it up here, making it a little bit clearer, a little bit better organized so that we can build on it in the next lesson. So what we need to do now is everywhere we were referring to the position, right? We are going to want to add agent dot in front of that, because position is now something that's included inside the agent object. So we kind of have like a few layers here. We have, if we wanted to get to the X coordinate of the agent, we'd have to say agent dot position dot X. Right? So, and that could keep going if you keep nesting objects inside one another. So I'm going to use my trusty copy and paste here and look for acceleration, velocity, right? And replace where we used single variables before, just replace agent. Okay? And at first glance, it seems like it's just making things more complicated. But once we try to build up and add more agents, doing it that way is going to make it easier to manage. I'm just going to comment out this show vector function because we're not really using it anymore. So I'm just going to leave it down there for reference, but I'm too lazy to go and add agent in front of all of these, considering we're not even using it. Okay, so now we're back to this place. So having done that, right, the other thing that we're going to do is we are going to tidy up the draw function a little bit as well. So right now there's kind of like three things happening inside the draw function. There's follow the mouse, okay? or actually technically 4 things. There's like apply a force. There's our little motion simulation, right? Motion simulation algorithm, very basic, right? Acceleration added to velocity, velocity shrunk a bit, velocity added to position. And then we have some rendering code that's taking our agent variable and representing it currently as a little box on the screen. But we could take this agent, which is really just a set of, coordinates. We could draw it as whatever if we wanted to. So we have some rendering code here. So why don't we clean up draw here and create separate functions for all of these sort of logical blocks that we are doing. Okay, so we'll start from the rendering code because I think that's a little bit obvious. So after we have our create agent here, let's make a function. Let's call it render agent. And we're going to take the code here and we're going to push it down there. All right. So the idea here is with this function, if you give it some agent object, okay, it happens to have the same name as our agent variable up here, but I'll show you at the end, we can rename this and it won't matter. Some agent object is going to come in. We will draw it as such. We will translate to its position, rotate to face the way that this agent is going, and then pop a rectangle right there. So this is how we render. And in fact, maybe we will also, we could decide to move these in, the stroke and fill inside the render if we wanted to. We can leave them out because they're going to just affect everything. So it doesn't really matter. So that's our render agent. Maybe in addition to that, we're going to create a function called move agent. So what does it mean to move? Well, it's these lines, right? This is how we move an agent. We're going to park this code in here. And I could have picked any parameter name, by the way. I just want to emphasize this, right? I could have called this A, but then I would have to go and rename all of this to A. So I don't want to have to do that. So I'm going to keep using the name agent because it's already written in my code. Then we have like apply a force. So this actually the motion here, the motion would be a good, this acceleration multiplied by 0. This really needs to happen maybe at the start of, or when we're done. When we're done here, we want to reset the acceleration. Okay, so we're going to do it after we've done our motion. We're going to always bring acceleration back to 0, so we have a clean slate in every frame, right? Think about, if you're representing the wind, for example, the wind kind of changes from one moment to the next. You might have times where there's no wind, times where there's wind. So acceleration is always going to be reset to 0, whereas velocity can build up over time with the friction, of course. So we're going to take that out and we're left with just this. Applying a force is basically just adding to the acceleration. But if we wanted to make it a little bit more clear, we could make it a function just for that, right? Let's call it apply force, agent force, right? And we're going to take this code, move it in there. And here we're going to say applying a force means taking the agent acceleration and applying this force to it. Okay, it may not always be diff, it could be any vector. So we're going to represent it like this. So what we're doing is we're kind of creating our own vocabulary of functions here just to help organize our program a little bit better and make our draw function easier to follow. The last behavior, the last thing we're going to package in its own function is going to be this little bit here. So follow the mouse. We're going to say, let's call this follow mouse. Okay. So if we have an agent, we want it to follow the mouse, we could do that. Put that in there. And the last bit of this behavior now becomes apply force, right? So we will say apply force to this agent, right? Like so. So we can use the functions that we create as building blocks inside other functions that we are writing. Okay, and now we're left with nothing at all in draw. Okay, so everything's gone. So let's rebuild this program using the kind of separate functions that we've created. So what happens in our program now? Well, we create the agent, okay, and then we're going to say render agent. There he is, right? Or she, we don't know. Then we're going to say move agent, but there's no motion because the velocity is 0. So let's then add follow mouse agent. And now we add our behavior. Okay. We could even, now that we've written it like this, right, we've cleaned up our draw a little bit, we've packaged things in functions. It also makes it easier to do things like we could say maybe only follow the mouse if mouse is pressed, perhaps. Okay. Makes it a little bit easier to understand. So now I guess you can't tell, but if I release my button, the it no longer follows the mouse, and we could play around with the friction here or the easing. I guess we could play around with the friction down here. Maybe we'll increase the friction. So if I leave my finger, it kind of bounces. If I stop following, it just kind of runs past. Okay. So we can play with these values to get all kinds of different styles of motion, all kinds of different types of motion. And yeah, so this code is a lot easier to follow now. We could also take target and diff, which really don't need to be global variables now that we're no longer doing this part here, show vectors. Why don't we just make them part of this follow the mouse concept? So let's define them locally and get rid of these. So, just cleaning house here a little bit, making our program slightly more better organized. So now we have an agent. In setup, we create the agent, we give it a starting position. Then in draw, we set some drawing parameters, and then if the mouse is pressed, we tell the agent to follow the mouse. Then we apply the motion code to the agent, and we draw it. Okay? And each of these individual actions has now been sort of packaged as its own function. Okay? Which will work, by the way, on any object which has a position, velocity, acceleration. So down the road, maybe we want to create more interesting simulations. We may have different types of agents, right? As long as they have those 3 parameters, they can all share the same apply force, move, right? They might have different render commands for different one of them. So we can build on this framework now that we've set a good foundation. All right. So this is probably a little bit longer than I was hoping it would be. We are going to leave it at that for this first example. In the next example, we're going to add one more thing. I would like to take a second to add, take these numbers here because it's going to be easy to lose them in the code. The easing for follow the mouse. Okay. Let's define those as global variables. And in the next lesson, we'll create a little interface so that we can also maybe tinker with them. So let's create those as global variables. And then in here, we're going to put easing. And then the 0.3 here, the friction. Let's create a variable called friction. Okay. So you thought I was done. I wasn't. Okay. And the reason for that is now it's a bit easier to try different combinations, right? We can tinker with those values, and I encourage you to play with this program and try changing the easing, the friction, just to see what happens. And we won't add a user interface in this one, but feel free to do that if you want to get some practice. In the next video, we're going to take this agent concept we've done, and then we'll scale it up. We'll create a whole group of agents, and then we will get their behavior to be influenced not by the mouse, but by Perlin noise. I'll see you in the next one.